Today I want to talk about really what is the majority of the geologic record from the early Earth, from this sort of prior to 4 billion period, and these are known as the Hadean zircons. So the Hadean is a time period of more than 4 billion years ago. It's what this lecture series is about. And zircons are an incredibly robust zirconium silicate mineral that has survived back where the oldest sample is almost 4.4 billion years old. So just to give everyone a quick reminder, the goal of the lecture series is to sort of see if the traditional view of the early Earth, that it was hot, dry, hellish, is accurate, or if in fact the geologic record disagrees with this, right? This is prior to the discovery of any geologic samples that are older than 4 billion years. So this is a sort of a classic view in the absence of any evidence the imagination can run wild. So I've introduced this slide previously, that you have a lot of things that you need for planetary habitability. And today I want to show you what the Hadean zircons can tell us about this and which of the questions are really answerable on this planet from the rock record, and which ones we just can't get at with the record that we currently have. So you have to be in the habitable zone, so you have to be close enough to your host star that it's not completely dark, that it's not, everything isn't frozen. You'd like to be somewhere with the stability field for liquid water, so you want to be not too close, not too far. You want to be in sort of the Goldilocks zone where the temperatures are just about right. Surface water is crucial, right? We all like to drink the stuff. All life depends upon the existence of liquid water. There's ideas that black smokers might have given us rise to the origin of life, and that the chemical reactions that involve liquid water are crucially important, including things such about early life. Interior water to the planets. The strength and stability of your rocky mantle, of your crust, is hugely dependent upon how much water is in the rocks themselves. And this you can see here, the strain rate. So this is basically the higher up you are. I'm sorry. Hope that fixes it. So the drier you are, the stronger it is, the harder it is to have things like plate tectonics, where you're bending tectonic plates, right? In the subduction zone, the oceanic crust is going from horizontal to getting bent down and vertical, to almost vertical in the mantle. It is also crucially important. We're going to spend a lot of time on this. How much water you have determines at what temperature your rock melts out. So the solidus, again, is the temperature at which you first start seeing melt. So here's the solidus here for a mantle. Here is when it's dry. You can see this is as a function of pressure, or if you prefer depth. So when you have wet melt, so when you have a lot of water, you're melting at much lower temperatures. So there's a huge effect, right? 400-degree difference at 100 kilometers depth between a dry rock melting and a wet rock melting. And this is going to become a crucial point throughout this lecture. So interior water has huge effects. The composition, you want something that that is actually pretty similar to what we have. Ideally you want iron for a core so that you can have a geodynamo. You want a silicate portion, so you want silicate for the mantle, then for the crust you want something that can concentrate these sort of incompatible elements, such as potassium, rubidium. For life you obviously want carbon, nitrogen, you want oxygen and water. So the planetary composition, right, if you don't have any carbon, it's kind of hard to have life as we know it, so you want some abundance of that. Planetary mass influences everything from how easy it is to retain an atmosphere to how easy it is for the body to segregate, right? If you are a really small body, it's, for example, forming a core is much more difficult just because gravity is much lower. The differentiation where you're separating the chemical layers is often gravity dependent. Convection has a huge gravity term in it. Impacts are both can both argued to be the giver and destroyer of life. Right? 65 million years ago, the dinosaurs were wiped out by an asteroid impact into the Chicxulub impact in the Gulf of Mexico. On the other hand, impacts can heat the surface of your planet, so they might give you places where extremophiles, the thermophiles can live. They can deliver elements to the surface that might not otherwise be on your planetary surface. Right? Carbonaceous chondrites have weight % carbon in them. They have a lot of water in them, so they might deliver elements to the surface that life needs to thrive on. Satellites are influence tides. They can be a little bit of a protective shield, but so they're important. Heating, you need the planet to be hot enough to sustain plate tectonics, so you need, if your entire planet is cold, it's kind of hard for rocks to move, and you just have one exposed surface layer that can weather away and hit an equilibrium. So you kind of want to be hot enough that you can have here or sort of convection zones drawn in where hot material from the base of the mantle is moving to the top. You want to give you this continuous flow. And on the other hand, if you're too hot, it might be inhospitable to life for other reasons, right? If you look at Venus, not a particularly pleasant place to be in under rainless sulfuric acid. So the heating is important. And finally, surface recycling. The fact that the Earth continuously exposes fresh material from the interior at places like mid-ocean ridge or ocean or volcanic arcs, you have material coming up. This is giving you continuously fresh material that you can weather. It's providing chemical differences, whereas if you have a planet that doesn't have any plate tectonics, at some point you're just going to react away and use up whatever material you can in the outer layer. And since you have no way of refreshing that, your planet is going to sort of die out pretty quickly. The geodynamo, hugely important, protects us from cosmic rays. It protects us from radiation. It protects us, our atmosphere, from the solar wind by deflecting it, and it helps you to keep your atmosphere. It's an open question when this started on Earth, but it is pretty clearly key to habitability today as we know it. So the green check marks are topics where the Hadean zircon record can really inform us. So it can't tell us necessarily if we're in the habitable zone, but we'll get into this next lecture. We're going to talk about surface water. They can definitely tell us, we'll talk about this today, about interior water, so water that is in the crust and below. They might be able to tell us about impacts, definitely about heat and the conditions at which they form. I'll show you that we can tell the temperature at which a zircon crystallizes. We're going to use that to infer surface recycling, and it might be possible, although this is the subject of ongoing research, that ultimately we can learn if there was a magnetic field on Earth back then based upon inclusions in the zircons. So, why zircon? Well, this is a slide that will hopefully convince you that zircon is the greatest mineral in existence. And partly the reason why zircon is, it's the only mineral that's older than 4 billion years that we have proof of, so we're kind of stuck with it, so we have to use it for something positive. So zircon is ZrSiO4. It is zirconium, silicon, and oxygen. It also takes in hafnium. In a previous lecture, I've talked about using hafnium isotopes to infer things about when the crust formed. Uranium, it takes 10 to thousands of ppm. So we can date this. Uranium decayed to lead is how we date the zircons. And here in the periodic table that you can see, the color coding is the compatibility. So something that's orange, there's a lot of it in the zircon. If it's white, then it really doesn't want to go into the zircon. So you can see that this is actually a pretty clean thing to deal with, because most of these elements simply don't want to go into zircon at any appreciable level. So since uranium decays to lead, uranium is highly compatible, lead doesn't go into zircon. So we don't really, when we do analyses, we don't find a lot of lead that isn't from the radioactive decay of uranium. That's great, it makes our life a lot easier. Hafnium, we've used the isotopic composition of. Titanium, the shading is a little hard to see, but titanium goes in just a little bit. We're going to use this as a thermometer to tell us the temperature of when our zircon formed. These here collectively are called the rare earth elements, from cerium up to lutetium. And these can tell you things about the magmatic chemistry. We're not going to get into it super much today, but we're going to focus on cerium in the next lecture because of its ability to tell us about the redox conditions. It's about to tell us if it was oxidizing or reducing on the early Earth, because cerium can exist in two valence states. And we'll get into that next lecture when we talk about surface and atmospheric processes. So there's a lot. So the point is, there's a lot of ability here, and the other nice part is it's able to survive a lot of stuff happening to it. A crystalline zircon is a hard thing to destroy unless you want to melt it. So a zircon that is crystalline, if you expose it to water, it doesn't really do anything to it. If you mess with it, it's really hard to actually destroy a zircon. The only way to really destroy them is if they have a high uranium content. The crystal structure can become destroyed by the radioactive decay. This is called metamictization, and it sort of turns your zircon into a glassy substance, and then it's really easy to destroy. But except for that process, kind of hard to get rid of your zircons. So they're a really robust time capsule for this process. So for example, things like, if you were to say, well, if I heat up the zircon and lead doesn't want to be there, is it possible for the lead to diffuse out of the zircon? And that might cause you some issues. Or can some of these other indicators here exchange with the environment? My zircon is sitting at, say, 600 C for a long time. Can I lose some of this chemical information? And the answer is, just quickly, the diffusion rate, so the ability of an atom to move through the zircon lattice due to thermal motion, is really, really slow, and it's a lot slower. So you're talking zircons are, say, 100 micrometers across, and things tend to move on the scale of hundreds of nanometers, less than a micron. So really the easiest way to damage your zircon is just to destroy it by melting it, by dropping it in a magma, or letting radioactive decay do its thing. But we can see if the crystal structure has been destroyed, so this one we can at least deal with. So I've said that the titanium contents are a thermometer. And the way that this is done is that people have done up here, these are lab experiments. So this here is the log titanium content. So basically, this is 10 ppm, this is 100 ppm, here's 1,000, and so going down. So in the experiments up to 1,000 C, sorry, this got put on top of each other. The 1,000 C and above, you can get in, 100 ppm, 1,000 ppm of titanium into your zircon. And at low temperature, these are natural zircons where we independently know the temperature of the system where it was grown. And you can see that they have much lower, and you can see that they fall on this really nice linear fin. So when you go out and you get a natural zircon, you put it in the lab, and I'll show you the instrument on the next slide, and you ask, what's the titanium concentration? And then you can basically go to the chart and say, we measured 100, this formed at 1,000 degrees. So this is one of the key pieces of evidence. People have, here's from the original paper I calibrated this, they're getting 780 C, 750 C. These are actually a little on the high side. Most of the zircons come in right around at 700 degrees C. There is one potential issue to this that has been explored. This is so the grayscale is a backscatter electron image. So this is a zircon, this is a different zircon. And what you can see is that there are cracks here, right? There's a crack running through it here. In this one, there's a crack structure sort of here, cracks right around here. And because titanium there's a lot of titanium in the world, when you have a crack, you actually infer higher titanium content. So this is the color coding here is titanium content. And so you can see the blue here, there's very little as you get on a crack. You have green, here you're getting red. And this is really, if you zoom in and do this even at a much higher spatial resolution, right? Here's a 20 micron scale bar, so about a fifth of the width of human hair, sort of around human hair. Here, 5 microns, really tiny, and you can see that the titanium is located in the cracks. So the temperature that you get, if you're not careful about some of these other factors, are upper limits. You're likely to infer a titanium content that is too high and not a titanium content that is too low. So you're likely in a natural zircon to overestimate the temperature rather than underestimate it. So that's just a caveat to also highlight some of the difficulty. The instrumentation, so here actually is here's a centimeter scale bar. Those tiny dots, those are zircons. So that's the sort of the size of sample that is being dealt with. So this is what you saw blown up on the previous slide here. That's one of those tiny dots. The instrument that is used for this is something called a secondary ion mass spectrometer. There's a picture of one. And what you do in it is you accelerate a beam of either oxygen or cesium. You focus it and you hit it at the sample. You can focus these beams down to less than a micron across. Reasonable analyses are done in sort of 5 micron sample. And then this is like shooting, this process is basically like shooting a cannon at an object. And then there's a whole bunch of stuff that comes when you shoot the primary beam, when you shoot the oxygen at the sample, you're knocking off a whole bunch of atoms, molecules, everything from the surface. And you can accelerate this to a known energy, bend it around, and then use a magnetic field to sort it based on mass. So here's, in the dark green, you can see this is the trajectory of what makes it into your detection. This is what gets counted at the end as an atom that you analyze. And here is something that has a slightly heavier mass. And you can see the magnet just can't bend it so it misses the detector. So this is how, in a sample, this is how you say titanium has got a known mass, titanium-48 being the most abundant isotope, so that you can basically focus this to atomic mass 48 and see how much there is in your sample. And these instruments have really been what have revolutionized the study of these zircons because they can analyze samples at such tiny spatial resolutions. Yes?
How destructive is this? So does it leave the material mostly undisturbed?
So this is a pretty typical picture of an ion probe spot. So you're thinking maybe a micron deep or less and maybe 5 to 30 microns across. So it is a destructive technique. That portion of material was removed and analyzed. You don't get it back. It doesn't damage the rest of the structure. It's really localized to just the material that you remove. You're removing about 20 microns across and a micron deep. The extra damage of the material that is left behind is on the orders of tens of nanometers. So it's basically a factor of 100 smaller than what you're analyzing. So you're doing very little damage to the rest of the zircon that is left behind. So it's not non-destructive, but it is pretty not destructive as far as techniques go. Other analytical methods would basically require that you take the entire zircon grain and dissolve it to analyze its chemical composition. So it is the least destructive technique that we have. And that's the cool part about it, is that you can do all of these analyses now on a single grain. That you can date them and get the chemistry, the isotopes, all of this on one grain, and you don't have to say, I want to do this analysis and now my grain is gone and I don't get to do the rest. So that's the cool part about it. Zircons are an awesome container, and I'll show you this. I just wanted to give, before I show it again on the next slide, a quick hint. Zircons are an awesome container for other minerals. So you have your zircon, and within your zircon, when it grows, it captures other minerals. So what I want you to focus on here is the blue bars. So these are inclusions that were found. Here's quartz, muscovite. These are found that are in isolation from any other feature. So around them is just crystalline zircon. There's no cracks or anything. The yellow and red will ignore now. And what I want you to notice is that the dominant inclusions are quartz, muscovite, and some biotite. And if you remember this plot that I had on a previous handout, right? This is already suggesting, muscovite is coming in at, 60 to 70%, right? This is suggesting quartz is in the high silica, same for biotite. This is suggesting that you're on this end, that you're on the felts again, that you're not at the basalt or komatiite at the low silica end. So this is suggestive. These are some of the minerals that you would find in granitic rocks, that you would find in the continental crust, rather than basalts and some of the sort of hot, dry, hellish rocks you would expect. So this has been in a previous handout. So let's just get a quick summary of let's just see everything that these have told us about what the planet was like. And here, this picture, this is the outcrop, this is the field site, this is in Western Australia. If you fly to Perth on the western coast of Australia, you get in a car and drive about 8 hours north. Then you've arrived. This is completely desolated in the middle of nowhere. That's what the rocks look like. Here's a more zoomed-in picture with pen for scale. These are the zircons. So these are the tiny dots that you saw in the previous one with the centimeter scale, where these are, a big one would be maybe a quarter of the way across across a fingernail or something. They are the long direction. So these are tiny. These are the titanium temperatures, right? So I told you that the titanium content tells us something about the temperature at which they crystallized, and we're going to use this is going to become a really important thing to let us infer, right? So we need a process that melts rock between 650 and 700 degrees Celsius. So this is the relative probability plot. So the higher you are, this is the bulk of the distribution here, 650 to 700, and there aren't any here at 900 to 1,000. It basically drops off by 800 degrees. So you need to be able to melt a rock at incredibly low temperatures, because 650, right, where this tail runs out, basically, is about the lowest temperatures at which you can produce molten rock, no matter what you want to do. So we need something 650 to 700 degrees, right? Here's a picture of a zircon, zoomed in. There's the 10 micron scale bar. So there's quartz, muscovite. So these are the very sort of granitic, high silica inclusions that you want to look at that tell you that these are really evolved rocks and not something like what happens when you just melt the mantle and you get a basalt. This slide is a little tricky, but it's just as an aside for everyone. You can, because you know the temperature, and because you know muscovite is really only stable at above 4 kilobars of pressure, you can broadly calculate how much heat is moving to the surface by saying at a depth corresponding to 4 kilobars, we have 650 degrees Celsius. So how much heat does that? And the point here is the expectation for the Hadean would be somewhere over here on this wall. So so we are having very, very low heat flows compared to what we'd expect. The expectation would be somewhere off on the other wall. We've discussed hafnium isotopes before, and the fact that this huge range points to a diversity of rocks, and that the apparent low lutetium-hafnium ratio, right, just to give the reference, this is the solar system's initial value. This is the part per 10,000 difference from the bulk Earth, plotted here. So these are all looking at a crustal signature because they are below the bulk Earth. The crust of the Earth has a lower lutetium-hafnium ratio than the bulk Earth, than the mantle. So, and then these point to some really low ones, and then this goes back. And then if you were to take these points and extrapolate back to when they could have been extracted from the bulk Earth, you were getting ages of something like 4.5 billion years, 4.4 billion years. So we need to form this crust early. Some of these other elements, right? So here's uranium over ytterbium and yttrium. These are some of the rare earth elements that I told you about that go into zircon. And the specifics of this is unimportant, but what I want you to notice is that the Hadean zircons do not fall into the field of the oceanic crust zircons. So at a mid-ocean ridge, you do make some zircons, but they look chemically very, very different. Kimberlites, these are places where you form diamonds. These are another setting. you do find some zircons, and again, they look very different. This actually looks like zircons that you find on the continental crust today. So that's telling you that the Hadean zircons did not form in a kimberlite setting, so they didn't form in a place where you get diamonds. They didn't form in something that looks like oceanic crust. They really formed in something that looks like continental crust. So the simplest possible interpretation of this data, if you found these zircons on the Earth today, is that you would say we have a subduction zone. So in a subduction zone, you have the oceanic crust and some sediments getting dragged down to depth, being heated up because it's hot in here, and then they basically melt and pop back up, and then you form zircon. So you all have this as a slide. So here, part of the evidence is the heat flow. The heat flow in a subduction zone is generally lower than the planet's average. So if the and it's generally about a quarter of what the average is. So that mostly works out, just as an aside. But the key thing is that this is the only mechanism that's capable of delivering a lot of water into the region where you melt. And it does this because there's sediments here that get dragged down with the downgoing slab that contain a lot of water, and these sediments will melt at depth and give you a melt that is saturated in water. So they give you a melt that has as much water in it as it is actually capable of holding. So this, just as for the today, in case the science class was in case you're not quite as familiar with the sort of tectonic regime, today the planet really, most of the geology on the surface of the planet is caused by plate tectonics. And that means that you have plates that are moving, so at a mid-ocean ridge here, you melt the mantle, you form new oceanic crust. This gets pushed to the side because you're forming new ones. It is more dense than the continental crust, so when it meets continental crust, it gets shoved down into the mantle and melts, and the sediments on top it melt first. And then you have, this is how you form mountain ranges. So here are the Andes in South America. There's a giant subduction zone off the coast here, where there's the oceanic plate is moving this way and being forced under South America. This gives you rise to the beautiful mountain ranges, the Andes. You have the black smokers at mid-ocean ridges. This is a sort of almost mini mountain chain in the bottom of the ocean. On the other hand, you can also have when two oceanic crusts meet, one can be forced under the other. This gives you what are known as island arcs. This is the Caribbean, for example, or a great example of island arcs. And so there's a lot of diversity on the planet, and what I want to convince you of today, and I have proposed, is that the Hadean zircons formed in a process like this, and that we had plate tectonics and this surface recycling, this regime operating all the way back to maybe 4.3 billion years ago. So people have, over the last, ever since plate tectonics became accepted, have argued about when plate tectonics started. And you have estimates all the way from 850 million years ago to, well, the camp that I would advocate for, to 4.2 billion years ago. And the difficulty with this is that plate tectonics destroys the evidence of its past operation, right? It takes material and puts it back into the mantle, melts it, and reforms it. So if you look at the crust of Mars, that is a very old crust. The crust of the Moon is very old. The Earth has a very young surface expression because of the operation of plate tectonics. Here are people using various estimates, so about metamorphic rocks that existed, so rocks that were heated to a certain temperature and pressure, isotopic evidence, and here's basically, I don't want to go into the details, but the point is, depending on what your favorite indicator of plate tectonics is when you say plate tectonics started. So if someone in here really likes ophiolites, this is oceanic crust that has gotten pushed onto some continental crust, then you like plate tectonics starting a billion years ago. If you're looking for isotopic arguments, you can go back 4 billion years. The issue is these are preservation These are of various difficulty when it comes to preserving them. So ophiolites are really hard to preserve. They get destroyed very easily. So the absence of older ones could simply be that they were destroyed, rather than having never existed. So there's a bunch of assumptions that are made in these various indicators that people go through. People have used what diamonds look like. This assumes that the temperature of the planet has been constant. So they say, look, there's a new type of inclusion in diamonds that forms at 3 billion years ago, and it doesn't exist before that. This is the onset of plate tectonics. Well, that assumes that the thermal structure is constant. People looking at how rocks form in arcs, so in the volcanic setting, also are assuming thermal structure is constant. They're also assuming that the composition is roughly constant. So people here have made arguments saying this is a reconstruction of how much magnesium was in the upper crust, shown in blue, and then from that they infer the crustal mass, and they say, look, back then there was a lot of magnesium, so it was a low silica crust, so it was something that looks like, basalt. And then in present day, it has very little magnesium, looks much more like a granite. And this transition happened 3 billion years ago. So this is when the crust grew and we started plate tectonics. Makes a lot of assumptions about the constancy of chemical composition. There's other explanations for this, including that magnesium content can't be used to infer silica. So there's a whole lot of these arguments, and basically it's a philosophical point to say that when I don't find my existence of something, right, if I don't find older diamonds with this, then this process didn't operate, because it could just be that the Earth was hotter back then. So this, to get into why the subducting plate is really the only model that works, we have to look at how rocks melt in the presence and absence of water. So this here, this is temperature versus pressure. So the surface, we're all the way to the left here at 20 degrees C and 0 pressure. So if you heat it at 0 pressure, and you have no water in your rock, this is the dry line, you are not going to melt your rock below maybe 1,100 degrees C. So at 800 degrees, you're going to have completely solid rock. It doesn't melt. At 1,000, you'll have solid rock. What I want you to look at is the line, this thick line denoting excess water. So as you increase pressure, you can start to get a lot of water in your silicate melts. This is in weight percent, so this is 5 weight percent, 10 weight percent, 25 weight percent water. And all of a sudden, the temperatures start to plummet. So you can start to melt rocks at much lower temperatures. And this is the key. This is only one specific type of rock. So let's go look at a whole bunch. Here is, everything from a basalt to a granite, and a basalt with a lot of water in it will melt at pretty similar temperatures to a granite with a lot of water in it. These lines here are the same as that solid curve. This is at the point where you stick as much water in as you physically can into the melt. And over here is what happens when they're dry, completely dry. So dry rock really doesn't melt below 1100 C, and when you increase the pressure, the problem just gets worse. Whereas if you have water, for a long time, the water goes into the melt and melts it a lot easier. This is because water is really good at breaking up the chemical structure of the melts and of the rock. So water is really destructive. So there's basically long chains of silicon and oxygen atoms attached to each other in a silicate melt. And the water gets in, the hydrogen gets in, and then there's silicon, oxygen, hydrogen, and nothing else can bond to it. And it's this breaking action of these long chains that explains why water has such an important role to play. So the fact that we get crystallization temperatures that are between 650 and 700 degrees really suggests you need a lot of water in the interior, in the rocks that you're melting. In that melt, you need to be basically at the case where you almost have as much water in there as you possibly can. Right? You can't do this in dry conditions. You never, under no conditions, will you have a dry rock be molten at 700 degrees C. So, the trick to this issue, this is one of the sort of the key issues, is that it's hard to store water in rocks. A rock, even with minerals like muscovite that can take up, you know, muscovite could be 4 weight% water. They don't actually store enough water so that if you take a rock that forms at these conditions and try to remelt it, you actually end up over here. Rocks themselves do not store sufficient amounts of water by themselves, especially at pressure, to melt and be at water saturation. You need an external source of water to do this, because as you're cooling your magma, the water wants to leave as steam. So as you're cooling it, decreasing temperature, the water leaves. So basically, what this is telling you is that you need a supply of water. Just to put this into perspective, up here, right, I said, you know, weight, I just want to put this in a little bit of context, right? So this up here is weight% water that you can dissolve in these melts. Here it is in mole%. So this is in how much of the molecules are, and just sort of counting molecules, is water. So at 1 kilobar, at not even very much pressure, you can put in, I call that 5 weight%. That's actually 40 mole%. So your melt, 40% of the molecules are water molecules. So this is not a tiny thing to add, because everything else, the silicon, the iron, all of these things are so much heavier that in a weight%, it really gives this misleading picture. You need a lot of water that you get, you know, you get to 10 kilobars, that is 70%, that is mostly water that you're dealing with, and there's very little silicon. So you can get, you require a lot of water, and you just can't get that from even the minerals that store the most amount of water. So if your rock was 100% muscovite, you wouldn't even be at water saturated melting at half a kilobar. And so we can go back and look at the previous phase diagrams and say those conditions really aren't possible. Your rock also isn't going to be 100% muscovite. It's going to have other stuff in it. So you need this massive source of water. If you take, to drive this point home, if you were to do a calculation and say, under what conditions, what's the most favorable possible condition without an external source of water, then you come up with this diagram here, where this is the solidus as a function of pressure and temperature. So this is below, to the left of this line, or below this line, everything is solid. Here you start producing melt, and this tells you how much melt you're producing. And the Hadean zircon pressure and temperature regime is here, right? We get this from the titanium temperature. We get this because we have muscovite, which is a mineral that is only stable at relatively high pressures. And this line here, the effective solidus, is basically, this is less than 3% melt. So even in the most favorable case, where you take a rock that has as much hydrous-bearing, as much water-bearing, muscovite, etc., minerals in it, you're not going to produce a lot of melt at the conditions where the Hadean zircon formed, or any melt. And this you can't move, it's stuck, because 97% of the rock is still solid. So only tiny fractions of it have melted. So under what are called vapor-absent conditions, vapor-absent meaning that you don't have this sort of excess water, that you're not saturated in water, you're not making any melt in any rock composition that is possible. So we can actually make we can actually find a modern analog for this if we go to the Himalayas to Tibet. So here is India, there's the Tibetan plateau. The rocks are going to come from here, so this is where they're coming, where they're hitting together. This is, this is the location of Mount Everest. Tectonically speaking, what has happened here is that India, 70 million years ago, started racing towards Asia and has been running into it, and the mountain range that you see here are some of the tallest in the world, or including the tallest mountain in the world, because India is basically shoving into Asia. Some of India is going under Asia, and this is producing conditions where we can see and find the sort of modern analog for these Hadean zircons. So what I want to talk about are two rock suites. The Tsona suite. This is a classic 20-million-year-old granite. It formed in vapor-absent melting. So it did not have enough water. It formed in a source that, while rich in water, was not enough to saturate it. And the aeronatural granites were formed by a process where excess water was being introduced into the magma from below because minerals below it were being destabilized and gave a flux of water. There's a nice picture, beautiful mountains, leucogranites, there's a person for scale. These are the ones we're talking about. There are these really white high silica rocks that formed by the process that I would argue the Hadean zircons formed at. So there's a couple of ways geochemically to distinguish these different melting signatures. So here's the rubidium-strontium ratio on a log plot, and the barium concentration. So if I start out in this gray field here, sort of the starting composition, and I move up in this direction here, then this is muscovite dehydration melt. So this is a source where a lot of water in the source is stored up in a mineral called muscovite, and it melts at about 740 C, and geochemically the evolution looks like this. You can see down here these arrows are the predicted, and you can see that's a pretty good fit. The rocks that are more interesting for our case are the aeronatural ones that don't show this same pattern. They move sort of more horizontally on this plot, and they fit in much better with this wet melting, which is a process that happens at 660 degrees C. So if we compare and we get zircons from both of these settings, then we can look at the titanium temperatures and we can compare them to the Hadean zircon distribution. The Tsona, the dehydration, so where you take a rock that has a lot of the water locked up in hydrous minerals, but no external source of water, no water coming in from anywhere else, you get temperatures where the peak is just too high. You know, this is peaking at 750. The blue here again is the Hadean curve that I showed you earlier. And the aeronatural is a much better fit. The peak overlaps. So a source where you have minerals breaking down and releasing their water below the melt and fluxing that melt give you a much better fit to the Hadean zircon and a really good one. So this process we can find modern analogs of, and it suggests that these formed under comparable conditions. Very quickly, there is one difference, is that for the Hadean case, the argument is that this is probably much more like a subduction zone than a continent-continent collision. But actually, here in white, this is depth versus temperature. So in white, you can see that we actually reach the same pressure and temperature places. This here is India getting thrusted under Asia. So just as a minor aside, even though these processes are different, because in one case you have a continent slamming into another continent, and in the Hadean it was much more likely sort of an oceanic type crust going under something like a continental. The physical setting is actually similar enough. So there's the overlap. People, because of the sort of the dry, hellish worldview, people have produced all sorts of other explanations for how these zircons could have formed. So I've shown you my favorite and the evidence that goes with it. So let me show you the other ones that have been proposed. So people have said, well, in mid-ocean ridges, you can form zircons, or in other sort of mafic rocks. And this is wrong because the trace element signatures that I showed you from these zircons plot in the oceanic field. And they give you crystallization temperatures that are just too high. These things crystallize at 800, 900 degrees, not 680, 700 degrees. So these are out because they make zircons that geochemically look very different from what we see in our record. People have proposed, well, if you need a lot of water, sediments can have a lot of water in them. So why don't we take some sediments and just drag them to depth? We just sort of have this being forced down, and then, so here's a plume coming out, making oceanic crust, and then it gets forced down somewhere else, and these sediments will have a lot of water. They won't have enough water, as I showed you with the Himalayan example. Even a rock where the sediments have a lot of water is not enough to give you the melting at the right temperatures, because it's just not enough water. So they would melt at 750, and the biggest problem is this material is headed down. It's headed down to the core mantle boundary, and it's hard to see how you find them in Western Australia 4 billion years later. They're on their way to being destroyed. So even if these would reach the right conditions, there's no mechanism for how they survive a journey to the core and then come back up. So that's kind of out. People have alternatively proposed that you can have something like the moon, where you have a sort of a basaltic crust. So here's the mantle, here is a basalt, low silica crust, and you magically introduce some water. They never say where it comes from. Maybe you can melt something and produce a sort of a melt of this basalt, but you don't have enough water to do this. The crystallization temperatures would be too high, and you wouldn't make muscovites in the inclusion because you don't have any potassium. Basalt is a rock that is really low in potassium. So that really doesn't work. And the other one that has been proposed is that impacts are the source of the Hadean zircons. And this was proposed that back early in the solar system's history, you had a lot of impact. You might have had planets rearranging their orbits, flinging stuff around, so they ran a model and said, look, we can make a lot of impacts happen at the peak. So this is how many zircons are crystallizing versus age. This is about the peak at 4.1. So they say, look, we've made an impact model that has a peak at 4.1. Maybe this produces the Hadean zircons. And basically, in their model, they're destroying the planet. This, if it was true, would be the dominant geologic process more than 4 billion years ago. Here, they're sort of showing you what the impacts are. And you're covering the planet in 20-kilometer thick impact melts over this time period. So you're covering, they say during sort of these, you're making sort of 3-kilometer thick impact ejecta. You're doing this 6 times. So you get about 18, 20 kilometers. The reason this doesn't work is I'm going to start to sound like a broken record. These rocks are too dry. They don't melt at low enough temperatures to do this process. So even if you could form zircons, which I would dispute, there isn't enough water. This does not explain, because you need to melt your rock, and you need an external source for this water, because rocks themselves don't actually contain this. So there's a lot of issues with this. The key one being, this doesn't tell us how we get enough water into the molten rock, and it would produce zircons that form at much higher temperatures than the titanium concentrations that I showed you. So basically, if you look, so people did this, Matt Wailiki did this for his PhD. Here's again the Hadean titanium temperatures, and these are impacts here in black. So you go around to impact melts that we've seen today, you look and you ask what temperatures did the zircons form at, and like you would predict, they formed at much higher temperatures, and we don't see this high temperature peak. We don't see any here where you have a significant portion of the impact zircons in the Hadean record. So they are not a dominant source. Other studies basically come to the same conclusion. Then people said, well, let's try and make... There was an observation of diamond inclusions in the zircons. At some point, someone reported and said, we find diamonds included in the zircons. This is really hard to do, basically, because diamond requires a lot of pressure. So diamond, here, this dashed line is basically diamond stability. Here is where the rocks melt, so you need a way to make these melts at 40. The previous plots stopped at 10 kilobars, which is 1 GPa here. So the previous plots where I showed you the melting happens and the pressure temperature conditions happen, if you want diamonds, you basically need to go a factor of almost close to 100 higher pressure to do this, and then you need a way get this material out very quickly. There's a simple reason for why this model doesn't need to be done. Someone looked at the zircons again and showed that the diamonds were contamination. The diamonds that they found, the zircons that they found the diamonds in were polished with diamonds in the lab. And during that process, they had cracks, and they simply pushed some of that polishing material into their zircon. So, because somebody looked in more detail and found that the zircon itself is actually, on this scale bar here, this is 200 nanometers, the zircon is actually invisible off to the side. This is diamond and epoxy. So if you believe in diamonds in these old zircons being formed 4 billion years ago, you also need to believe in epoxy being in zircons that old, which is blue. So that's kind of hard. So we don't really need this. So with all of these other mechanisms that people have proposed, and people will presumably continue to produce nodes, there's a lot of stuff that they have to explain. And I kind of wanted to finish off with this. We're pretty close to the end here. If there was evidence for a geodynamo back in the Hadean. So the way that this is done is if you look at a mineral, certain minerals, especially iron, will remember, right? You have your bar magnets that you play with. If you heat a material up and cool it in the presence, through the Curie temperature, in the presence of a magnetic field, iron, for example, will remember if there was a magnetic field then or not. So you can come back at much later time and look and say, if my bar magnet, this was produced in the presence of a magnetic field. So you can do this with natural samples. So this is a research area called paleomagnetism. And one of the things is we have evidence for a geodynamo back to about 3.5 billion years ago. We have no record. Zircons themselves are not going to be good for this. They are not, they have no useful magnetic properties. But zircons include all sorts of other fun minerals, including some iron oxides, that might give you a hint. The problem is, so this has actually been argued. Tarjuno et al. In 2015, they got some zircons, they dated the zircons, they got a magnetic field value for this and said, look, there was a geodynamo. This measurement is problematic because, for two reasons. One, you don't know, the Curie temperature is basically 600 degrees. So if your zircon has more recently been above 600 degrees and cooled down through 600 degrees, say it did that 1 billion years ago when we know that there was a geodynamo, you could date your zircon, and the zircon is 4 billion years old, but the magnetic field was imprinted on it only 1 billion years ago. So they didn't show that these are actually recording that the zircon has remained below this temperature for below 600 C over its entire existence, because this is actually really difficult to do with zircon, because zircon is this robust mineral where really very little moves around, so it's not hard. It's not obvious how you would show this. And the second thing is, you can see here, these dots are individual zircons, and these here, this is the magnetic field strength. So 0 is this color. Zircons do in fact have things that show strong evidence for magnetic fields. Here's one with red. This tends to be on the exterior of the grain, and the problem is almost every Hadean zircon has a lot of iron oxide in cracks and such that is secondary. So it is, even if you could show that the zircon has remained cold, a lot of the iron oxide is basically surface contamination, and their measurements did nothing to rectify this. So this is work out of Ben Weiss's lab at MIT that is trying to track this problem. And yes, you can find magnetic evidence, but you can see it's not generally coming from the interior. The vast majority of it is coming from the surface of the zircon, and that this is a massive problem for these studies. So this hasn't really been demonstrated. As a quick thing, the only possible way to maybe tell this is that lithium moves really quickly in zircon, and if you have something that preserves the sharp gradient, this is the lithium concentration here, and you can see that this is a really sharp feature in lithium in the zircon shown here. And basically, lithium is mobile at above 600 C or above 500 C, basically. So if you can find really fine-scale zoning in lithium, maybe you can argue that because you have preserved this zoning and it hasn't spread out and become homogeneous by diffusion, that you were below this temperature. But this work is still ongoing, hasn't been completed, and so there has been one claim of a geodynamo, but this is highly contentious to say the least. And as just as a quick thing, everything I was talking about today comes from the Hadean zircons found here in Western Australia. People have reported sort of individual ones elsewhere. One has been found in Greenland, one in Canada, a handful in China, 2 in South America, and to find more is an enormous effort. So these are studies where in order to find, zircons, you're going to have to basically date somewhere on the order of thousands of grains to find a single one that is old enough. So this is because the yields aren't as good as they are in Western Australia. So the ones from, just to give you a random example from China, they show ages going back to 4.1 billion years. So you can see here, there's a uranium lead age on this zircon, 4.1 billion years. Here's something around 4.1 billion years. They looked at the titanium temperatures and said, look, they're like 750, 800. They still look continental in this uranium ytterbium plot versus yttrium plot that I showed you earlier, right? The Jack Hill zircons all plot, the Hadean ones from Western Australia that I've been talking about all plot in here. The oceanic crust is well resolved, and basically they're saying, look, ours also look continental, so that in China during this time period we're seeing evidence of some continental crust, but that you don't need as much water because the temperatures were hotter. So it might be a different setting, but these are only 2 zircons, and everything else I've been talking about from the Jack Hills in Western Australia, we have thousands of zircons to look at. So this is really promising future work that we might be able to extend our global reach and the chemistry that we can pull out from these samples. So there's a sort of a summary slide, and I can take any questions. Thank you.
You said that new materials had to be convected out to the surface in order for the planet to be live, I guess to support life or something?
Yes.
Why is that the case? The material that goes up there can be recycled without...
The rocks that come out of the mantle are not they're not chemically happy at the surface of the Earth. So a nice fresh mid-ocean ridge basalt, if you expose it to say CO2, it will weather and form carbonate. So it'll actually lock up and draw down carbon dioxide over long time scales out of the atmosphere. If you let this process run to conclusion, where the entire surface has been reacted away through these processes, then the processes stop happening. So the issue, so this is, imagine the simplest analogy I can give you is farming, right? If you continuously farm and deplete the nutrients in a farm field, eventually it'll be out and you need a fresh source of material. You'll sort of, the land won't be as habitable anymore because you've taken the nutrients and those elements out of the rocks and you can't replace them. So if you have a setting like Mars or the Moon, where you have just this one surface layer that you're dealing with, if you don't have a mechanism of continuously replenishing that, then you're ultimately going to take, if there is life, it'll just sort of take whatever the nutrients are out of that surface layer, and then it'll run out, because at a certain point, it just can't infiltrate deep enough and do it. So the easiest way to do this is if the planet simply brings you this fresh material to the surface. So I would argue it's one of the keys to habitability. One of, in my view, requirements is that for life is that you have some sort of process of actively refreshing the materials on the surface to give, to continue to allow a lot of the chemical interactions to happen that happen. For example, drawdown of CO2 out of the atmosphere. Other questions? Yes?
Well, with that statement, if you have very small life, you can still have life, but if you have, you don't have to refresh the nutrients, so to speak, if you have very small life and a lot of it that doesn't consume a lot of it, you can still have it for a very long time.
This is true, but I would argue that most life is really good at expanding and reproducing, right? So if you have a pop, right? From a biology point of view, if you have something and there's a lot of food, right, or there's a lot of sort of available stuff to deal with, it's going to expand until it runs out. So I would say that it's unlikely that you might have a little bit starting out, but at some point through evolution, right, it would adapt to its local environment, and at some point you will exceed the carrying capacity. So I think that might be possible for a time, but I would argue that the process is self-limiting in that at a certain point, everything that you need on the surface or that is able to chemically react will do so, and then you have basically killed off the life on your planet. Yes?
Any idea why Venus is so different?
That is an excellent question. We don't know why it evolved to be so different, right? It is different today because the atmosphere retains a lot more heat, right? It has the runaway greenhouse effect this planet hasn't had. So basically, if you were to take sort of all of the carbon sort of on the planet and put it as CO2 in the atmosphere, you would retain a lot of heat in your planet. Your planet would become hot, and you'd sort of end up like Venus. It is an open question why Venus ended up this way. It's possible it's a little closer to the sun, so maybe the atmospheric chemistry is just that sensitive to, you have a little bit more heat, so you end up driving it away that way. Maybe there was a catastrophic event early in Venus's history. I really don't know what the answer to that is, and I don't know if anyone can tell you why it ended up being so different than it is. But it is different just because of the atmosphere has so much more carbon-bearing CO2. It has so much more greenhouse gases in it that that it retains all this heat, and that it has something like a surface temperature of 400 degrees C or something. So, yes.
If I read this right, back some time ago, when there were probes going to Venus, when they measured the temperature through the atmosphere, the temperature at 1 bar, remember it's 93 bars of the surface, the temperature at 1 bar would be very similar to what Earth would be if it was at that position in the orbital mechanics of the solar system. Was at that distance. So pressure would apparently have a lot to do with it.
It is certainly true that there are places in the atmosphere of Venus that are pretty friendly from a scale of Venus that look very similar to the Earth. This has been used, people have proposed missions to Venus for that you can basically float a hot air balloon on Venus and it could kind of exist and study the atmospheric chemistry. But I would say the origin of Venus's atmosphere is, because we just don't have any data points on it, is still fairly unknown. So certainly the pressure and the temperature are in some sense related, is a huge component, but I don't know how it ended up there. Yes?
Well, did Venus ever have plate tectonics, or we don't know that?
We don't know that whether it did or not. There is some evidence of surface topography. The crust, as far as we can tell, looks pretty uniform, like basalt. But again, these are hard, sort of remote sensing measurements that people are making. There's some arguments about whether or not basically Venus has not had plate tectonics. So one of the stories goes, Venus hasn't had plate tectonics. It's had a sort of solid rocky lid. In the interior of the planet heats up, heats up, heats up, and eventually the crust, this becomes unstable and the crust gets replenished. It gets destroyed and the entire planet gets resurfaced. And so this is thought to happen, and that's probably the most accepted idea on Venus and its surface. So that would speak very heavily against it having plate tectonics, because plate tectonics is a great way to get heat out of your planet from the interior. Most of the heat loss on the Earth today is at mid-ocean ridge. environment simply because you have molten rock being introduced to cold water. And that is a really great way to cool your planet off.
Since so many of these experiments have a wide latitude of questionability, at the end of this course, are we going to be able to say with some degree of certainty what Canadian life really did look like?
We're going to get in, so I would like to ask you to hold off to the life question for 2 more Saturdays, and then we'll study life and if there was evidence for life back then, and how we try and answer this question.
Okay.
So, answer is coming. In the back?
Why is it that Western Australia is so, has such a unique outcropping, such an old outcropping?
We don't know how unique it is. So Australia is unique in the sense that a lot of Australian rocks have been dated. So Australia is a country that economically has a lot of mining, and mining is a huge component of their economy. So the Geological Survey of Australia goes out and tries to date every rock in Australia. They try and study every rock to see if they can discover new mineral deposits. So it is certainly one of the better sampled places. It also doesn't, it's generally pretty deserty, so it's easy to get rocks, right? If you look at the Amazon rainforest in South America, it's kind of hard to go out and get rocks because you have a rainforest growing on top of it that you've got to deal with. So Australia is perfect from an exploration point of view for rocks, so that's certainly one reason. The second is it preserves some fairly old crust. So the rock itself that you see pictured here is so the rock itself here, this rock is 3 billion years old. Australia has had the good fortune of being pretty tectonically isolated. So there's not a whole lot of subduction or other processes going on. It's just been kind of chilling out there and hanging out for a long time. So it's been a pretty sort of isolated, stable place. You also find a lot of rocks up in northern Canada, which has also been pretty tectonically stable, and Greenland has a lot of old rocks. So the zircon collection for zircons that old is at present unique, but I would be willing to bet that that is due to sampling and coverage and exploration rather than due to any sort of geologic factor. The other thing is if you go to the US government, if you go to the National Science Foundation right now and say, I want to date a bunch of random rocks in Canada in hopes of maybe finding some old zircons, you're going to get laughed out of the room. Scientific funding has to be justified in terms of scientific returns, and wanting to go fishing is not, in hopes that you might find something, is not something that's easy to get funded. So it's not actually easy to get money to find these new locations. They're generally discovered by accident. Somebody says, I want to do this interesting work here. I want to understand how these rocks formed or how this happened, or if there's, maybe some sort of thing economically valuable here. We have reason to think this. Then they get money and they find these as an accident, basically. So the process has been more luck-driven than anything.
I also had read some time ago that the early Earth, when it first formed, the atmosphere was about 1/3 carbon dioxide. But no runaway happened after that. So maybe we're immune from a runaway greenhouse.
We do not. It is hard to say how much carbon dioxide was in the early atmosphere. We don't have really good samples from that. People, for the Hadean, so anything older than 4 billion years, it's almost impossible to say what the atmosphere was like. We'll get into this in the next lecture a little bit. There's some very basic constraints that can be provided, but it's hard to say that there really was a lot of carbon dioxide. We don't have evidence one way or the other. People have claimed this. This gets invoked in the context of the faint young sun problem, where basically 4.5 billion years ago, the sun was thought to output only 70% as much as it does today. And if you then do the calculation, the planet would be frozen over. And so people try to do climate models and understand, well, could an atmospheric effect have solved this for us if it made it, warm enough to have liquid water? This depends a lot on how sophisticated the climate model is. So a lot of this work has been done with one-dimensional climate models. So they basically say, my planet is a column, and I'm only going to consider that sort of depth effect. These tend to make it very hard to keep the planet warm. On the other hand, if you start running sort of 3D simulations, which are computationally a lot more expensive but are a lot more accurate, you find it's much easier to keep your planet warm. So there's a huge array of debate, and part of it comes down to how computationally intensive your model is. And running a 3D climate model takes a lot of computation power, and there's a lot of free parameters in terms of what the atmospheric composition was. So you're not just going to have to run this once for your atmospheric composition to see what it was like, but you're going to have to do this a lot. So this is why people like the 1D models.
I tend to disagree with your assumption that the limitation of life is going to be on the nutrient concentration or nutrient availability. You mentioned the Amazon. Very depleted lead-rich soils there. And yet almost all of the nutrients are bound up in one form of life or another. The other possibility, of course, is that you can still have expansion by life actually digging into the crust at some point, sooner or later. I mean, evolution probably would drive it that way. The critical factor, I think, in that case, in any of these cases, is the energy flow. And how can you get energy into those areas where life could be scavenging or mobilizing whatever nutrients might be available. In other words, there could be theoretically a life zone which is digging into other zones to get whatever it needs. That's a nice theory. Of course, there's an awful lot of hypothetical components that have not yet been either described or tested. However, that there is a refresher tendency within the Earth through mountain building, weathering, etc. I mean, that's very, very well established. The real key, of course, would be to find life elsewhere and compare it to what we've got here. That is not out of the question, considering the astronomical work that has been done actually fairly recently. However, there's no evidence. The same problem with your zircons. You seem to have a great deal of data from a relatively small area, which is nice, and of course, many of these things have been done quite well, but the other zircon locations really do need to be found in order to justify some of the assumptions that you're making.
There's absolutely a sampling problem, right? Almost everything is from one place. We don't know how much of the surface is being sampled in this. Catchment basins, right? If you are a mountain and you're eroding stuff off, that can be transported really long distances. So, for example, if you look at, if you go to the Gulf of Mexico and look at the Colorado River, or sorry, not Gulf, if you go to Mexico where the Colorado River comes out, you will find zircons being transported thousands and thousands of kilometers coming down. So these zircons are all from one place, but basically each zircon could be sampling a different part, or they could all be sampling a similar thing. They have a huge age spread. If you look at right, they go back to 4.3 billion years. They go to 4 billion years. They even get younger once we get to the younger ones. The geodynamic settings that we know of tend not to exist for that long. So this is long on a scale of, for example, arcs tend not to exist for 500 million, a billion years. Oceanic basins open and close on those kinds of time scales. So it is possible, we don't know. So it's possible that you're getting a really good sampling of the planet, or it's possible that you're basically sampling the same thing over and over again. There's a huge range here in the... battery's up, I think. The only way to answer that is to go to other locations and find more zircons. That is certainly part of it. The thing to your life that I take is, at a certain point you will run out because the thermal structure of your planet. You can only go so deep before it becomes really hot. Geotherms are on the order of 30 degrees per kilometer. So especially if you do this in a place like the Earth, you're going to get into really hot temperatures relatively quickly. So at some point, you will deplete that outer layer. And as your planet starts to cool, you're also going to simultaneously, the heat loss from the planet and things that you might put into the air. I think you'd run into difficulties with this. I think at some point, the question is how quickly and how much is available, but at some point, without surface recycling, I think it is a finite thing. And the thing to your Amazon point is, the point about the soils is well made. The Andes are right next door, and there's a giant arc sitting right next to it, and a lot of the runoff from that is getting introduced into the system. So you actually, the Amazon rainforest is a great place where you might have locally depleted nutrients, but you also have this great, fantastic source right next door, and that sheds into the Amazon. So it's not as the problem with studying it is that looking at one part in isolation is difficult, since it's a whole sort of global system. And I think on that, I want to thank you, since I'm out of batteries.